Okay. So we are just a few minutes early here, but I figured it couldn't hurt to pop in. I'm having a hard time finding the Zoom recording from our meeting last Friday. So Django just came by the office hour asking for me to upload that. And when I went looking for it, it was nowhere to be found in my local machine's Zoom folder. So instead of that, what I'll do here is post or share with you guys. Here is a recording from last fall. Honors class. So if you're looking for the recording of our class on Friday, I'm having a little bit of trouble finding it myself to upload, but you can watch that as an alternative because it does cover the same material. I think what's going on here is that the OneDrive application from Santa Fe likes to, for whatever reason, download and rearrange my Zoom folder. So when I purge it, when I delete a bunch of old stuff, every now and then OneDrive says, oh no, don't do that. And it just like re-downloads all the shit that I deleted from the cloud. And it might have pushed out some stuff that I had before. Or is this it? It was 25? Is that what we're looking for? Oh, so weird. Here it is. Okay. Never mind. All right, so I did find that file. I'll go ahead and upload the original. But if you want something to watch in the meantime, the link in the chat there is the same content. All right. So that out of the way, I guess I'll go ahead and grab some water while folks trickle in, and then we'll get started. Okay. So for those who came in just a second ago, having a little bit of trouble getting the video uploaded from last Friday. For whatever reason, Microsoft OneDrive decided to completely rearrange my Zoom folder and download a bunch of shit from last year that I had long deleted, burying the stuff that I need to find in a massive pile of ancient crap. So if you look in the chat there, you'll see a link to my uploaded recording of last fall's lecture covering the same material. That's from an honors class, so we covered the mean value theorem just before going into 4.3, but that link actually starts right where we begin the first derivative test type stuff, the increasing decreasing theorem. So if you're looking for a recording, you can follow the link in chat, and I will try to exhume the recording from last Friday and get it uploaded as soon as I can. In the meantime, here today, we're going to continue pushing in that direction we've been pushing, where we want to have a function handed to us and without any sort of graphing utility, get a really nice graph of that function. This is going to come from finding where the function is positive, negative, x-intercepts, where the function is increasing, decreasing, mins and maxes, where the function is concave up, concave down, and inflection points. Once we have all of those things together with the end behavior for the function, we will be in good shape to draw a really, really nice graph by hand without using any graphing software. That might seem a little bit silly given that we have things like Desmos, but it's not just to produce graphs, it's also to answer, kind of curious, interesting questions about the function. It just happens to be that thinking about the graph is the right way to get there. So we're learning it through this lens of how am I going to sketch a graph by hand. So last time we went through 4.3 and we learned how from the derivative we can determine where f is increasing and decreasing, which will tell us mins and maxes. We learned how to use the second derivative to say where f is concave up and concave down, and where that second derivative changes sign, we have these things called inflection points. And from there, we had a shitload of pretty nasty problems. You guys have seen that those problems can take quite a while. There's a lot to them, depending on how ridiculous the algebra gets. I think it would be fun to kick the day off just with something like one of these very open-ended sketch a graph that satisfies the following condition questions. I'll tell you that my exam 2 in Calc 1 always has a question like this. And I know that WebAssign does a terrible job of getting you ready for these because it just gives you 4 graphs and you click until you get the right answer. Not at all the same thing as looking at these conditions and drawing them yourself. So I want to just take a look at one of these 27 through 31 type problems here and see if we can conjure a nice graph ourselves. Let's take a look at 30, this being an even numbered exercise. If you're working out of the textbook, you won't have that. Before, let me go ahead and get our title card up. So this is MAC 2311, section number 004, which is a Calc 1 class. The date today is the 28th of February, 2022. And what we're going to do today is we're going to talk about something called L'Hopital's rule. And the class of objects to which L'Hopital's rule applies, which are called indeterminate forms. But first, one more example. From section 4.3, which is the section we were doing on Friday. So again, problems like these show up 100% of the time on my exam 2. I give you some conditions on f, f primed, and f double primed, and I ask you to just sketch for me any graph that satisfies these conditions. Very, very open-ended and very much not good WebAssign problems because you can just click until you get the answer they want. So I'll go ahead and do number 30 here. We want to sketch the graph of any function f satisfying, let me copy these conditions down, f primed of 0 equals f primed of 4 equals 0. So that tells us we have horizontal tangent lines when x is 0 and when x is 4. We're also told that f primed of x is 1 for x is less than -1. We're told that f primed is positive for x is between 0 and 2. And f primed of x is negative on a collection of intervals here. Says if -1 is less than x is less than 0, or x2 is less than x is less than 4, or if x is strictly greater than 4. Okay. The next set of conditions there is that the limit as x goes to 2 from the left, again, I'm just reading number 30 here, limit as x goes to 2 from the left of f primed of x is positive infinity. The limit as x goes to 2 from the right of f primed of x is negative infinity. So there's some sort of cusp going on at 2. And then we're told f double primed is positive. So that's 1, that's 2. And then f prime primed of x is greater than 0 if x is between -1 and 2. -1 is less than x is less than 2. Or 2 is less than x is less than 4. It takes more space to write the problem than it does to solve the problem. F double primed of x is negative if x is greater than 4. Okay, here are all of these conditions. I put them into a bulleted list. The first bulleted list are some conditions on values of f primed. The second bullet here is something funny happening at 2. And the third bullet here are conditions on the second derivative, f double primed. The trick to this problem, and all problems like it, is to make those number lines, kind of pretending like they gave you f and you took the derivatives and found the critical numbers and tested points or used the multiplicity trick, make the number lines, and then we'll sketch from there. So I'm going to use this first set of conditions on f primed here to make a number line for f primed. I'm going to use this set of conditions on f double primed here to make a number line for f double primed. And then I'll see how I can sketch a graph that has those features and also meets these two requirements here. So again, we're going to begin with two number lines. And in section 4.5, when we go to sketch graphs of functions by hand, the main thing will be to cook up these number lines as we did in 4.3 and then draw the graph from those. So where is interesting shit happening for the first derivative? Well, f primed of 0 and f primed of 4 are both 0. Automatically 0 and 4 are critical numbers. Looks like something interesting might be going on at -1 as well, right? Because f primed of x is equal to 1 for x is less than -1. Okay, where else is stuff going on? F primed is negative from -1 to 0, from 2 to 4, and from 4 onwards. All right, so I'm going to put 0. Let's see. -1, 0, 2, and 4 on the f prime number line. -1, 0, 2, and 4. Because all of the sort of interesting things happening to the derivative either happen at those values or change at those values. Those are the inputs that show up in the conditions on f prime. And then I'm going to fill out the signs here. So we're told that f primed is equal to 1 for all x's less than -1. So specifically, f primed is definitely positive there. And in fact, we're told that f primed is straight up equal to 1 everywhere in this region. We're told that f primed is positive between 0 and 2. So that's in here. F primed is positive in here, although I don't know the value exactly, just positive. I'm told that f primed is negative between -1 and 0. So we're negative in here. F primed is negative between 2 and 4. So we're negative in here. And f primed is negative to the right of 4. So we're negative over here. So here's my number line for f primed. I've inserted this bit of info that f primed is identically 1 over here. And yeah, that's good. So we are increasing, decreasing, increasing, decreasing, decreasing. So some things I can say for sure. I have a max here. I have a min here. I have a max here. Right, where we go from increasing to decreasing, gotta be a max. And where we go from decreasing to increasing, gotta be a min. Something cattywampus is happening at 4. We'll see if we can figure what that could be. The other stuff I would make note of, horizontal tangents at 0 and 4 guaranteed. So there's definitely an HTL here. And there's definitely an HTL here. Although the HTL at 4 would not be obvious from the sign information, they told me that f prime of 4 is 0. Right? This tells me the second HTL. This tells me the first. All right, the only first derivative information I haven't incorporated yet is this stuff. We'll get to that in just a minute. Let's go ahead and draw a number line for f double prime. So places where interesting stuff is happening for the second derivative, -1 to 2. So -1 and 2 are interesting numbers there. 2 and 4, and then 4 here. So it looks like I just need -1, 2, and 4 on this number line. And I'll try to make them line up with the place I put those on the number line for the first derivative. I usually find that pretty helpful. Chop up into regions. And then I have concavity information. So I know f double primed is positive from -1 to 2. So everywhere in here, f primed is positive, which means we're concave up in here. And from 2 to 4, right, we're also concave up here. So f double prime is positive here, and we're concave up. And then f double prime is negative to the right of 4. So that means we're going to be concave down here. And you notice there's a region from the f double prime number line where I don't appear to have information. Can anybody help me with that? What's going on to the left of -1?
It's just a straight line.
Yeah, we were told that f primed is identically 1 in this region, which means f double primed would be 0 in this region. In other words, here, let me fill it in like this. I'll say f double primed of x is 0 everywhere in here. Neither positive nor negative. So there is no concavity information there. Yeah, if f primed is 1 everywhere here, that means f is a straight line with slope 1 everywhere in that region. So there's no concave up or concave down. All right, we're ready to sketch. There is one thing I have not accounted for yet, and that's this stuff. Generally, when we pass from the number lines for f prime and double prime to trying to draw the graph, I like to draw one more line that I call the shape of f. So increasing concave up, decreasing concave down, that sort of thing, right? On this number line go all of the numbers from the previous ones. So from negative infinity up to -1, the first derivative is constant. It's the constant number 1. So we're not concave up or concave down. We are increasing. For the shape there, I would say the function literally just looks like this, right? A function whose first derivative is the constant function 1 is a line with a constant slope of 1. Between -1 and 0, from the number line for f primed, I see we are decreasing. And from the number line for f double primed, I see we are concave up. So in this region down here, I should draw something that is decreasing concave up. That looks like this. So decreasing from the f prime line, concave up from the f double prime line. Next, I'm looking at the 0 to 2 region. Between 0 and 2, f prime is positive, so I'm increasing. F double prime is positive, so I'm concave up. So this is going to be increasing concave up, which looks like this. Between 2 and 4, f primed is negative, so we're decreasing. F double primed is still positive, so we're going to be concave up. That's decreasing concave up again. That looks like this. And to the right of 4, we are decreasing and concave down, which looks like this. Now now that we have this shape, we can kind of try to label what's going on at each of these things. This is for sure a local min. This for sure is some sort of max, but it's also going to be a cusp. You see, if I try to join two pieces together that look like this, then the only way to join them together continuously is with a pointy cusp shape, something like that, right? So there's going to be a max here, and it is a cusp. At x equals 4, we have a horizontal tangent line, but no min or max. And you can imagine kind of joining two pieces together that look like that. Something like this would do the job. Where you can get your horizontal tangent, just briefly horizontal tangent in here, without actually having a min or a max. This guy over here, I initially labeled as a max because we're going to go from increasing to decreasing, but he's going to be a little bit of a wonky looking max. But I'll continue labeling him as a max. He is a max. He just doesn't have the normal hill shape. So here's what we're looking at. That's the shape of F. They never specified any x-intercepts, so I could have some or not. It's up to us. They never actually specified a single specific value for the original function, just values behavior for the derivative. I'll mark here -1. This will be 1, 2, 3, 4, something like that. Everywhere to the left of -1, I know I'm going to be doing this straight line slope 1 business, because f primed is supposed to be the constant function 1, which means that no matter where you look along here, the slope of the tangent should be 1. Only way that's possible is if the function is linear there. They did say they want the function to be continuous. So when I join this up with the next piece, it's going to do something like this. And maybe I poke down through the x-axis there or not, totally up to you. but I have to have this decreasing concave up shape, decreasing concave up shape. And then I need to join to this increasing concave up shape, which we're going to continue until we get to 2. Maybe something like this. And we're supposed to have a vertical tangent here. But again, the function needs to stay continuous, so we have a cusp. And then we continue with this shape, decreasing concave up, until we get over here to 4, where I need to briefly have a horizontal tangent, but then transition to decreasing concave down, which could look like this. And there we have it. So I didn't label these. This is 2, this is 4. Here's your horizontal tangent line, here's your cusp, here's your normal looking min, here's your weird looking max. Now these can be challenging, right? These can be challenging. So when you bump into these in WebAssign, I know it's tempting to just click till you get the answer and then move on because there's other work to do. Solve a few of them for real, right? I promise I wouldn't put them in there unless they're important for your understanding. So I know that homework set is a big one. If you need more time on it, don't hesitate to ask for an extension, but make sure that these problems you're really working them out. Questions on how we got to this graph here?
Is the point that 2 gets to stated? Is it like given?
I don't think so. No, I don't think they specify any exact values. So do they give us f of 2 anywhere? No.
So then it's just kind of like you don't need exact points, but the shape needs to be right.
Correct. Yeah, they didn't
Okay.
specify y values at any of these. So you could drag this whole picture up or down, and as long as the shape stays the same, or you could stretch it up or down, and as long as the shape stays the same, that would still be a correct answer. There's infinitely many correct answers here. But this is one of them. I do want to draw your attention to the cusp really quick. That statement that they said the limit as x goes to 2 from the left of f primed of x is positive infinity, and the limit as x goes to 2 from the right f primed of x is negative infinity. That's saying that these tangent lines here are tending towards verticality, right? So that's how I know that that's a pointy cusp. The other hint that that's a pointy cusp is that I'm told to continuously join 2 pieces like this. And the only way to do that is with a cusp. So they could have omitted these and just given me the information to get these, and I could still deduce that the graph shape would be this. Okay, any questions on this one? Okay then. In calculus, one of the things that we're constantly trying to do is sort of wrestle with infinity, right? We're trying to understand like what infinity means, and to a certain extent, we do arithmetic with infinity or algebra with infinities. So this is section 4.3, or sorry, 4.4, which is on indeterminate forms. And L'Hopital's rule. Insert your favorite joke about L'Hopital's rule sending you to the hospital. L'Hopital is actually a dude. He was a guy. and it's called L'Hopital apostrophe S rule because it's his rule. The truth is that he actually didn't come up with it. One of the Bernoulli brothers came up with it. Jacob and Johann Bernoulli came from a mathematician family. I think it was Jacob. And L'Hopital, wanting to be more famous, purchased the theorem from Jacob Bernoulli and published it under his own name, which is a weird thing to do, but it happened. What L'Hopital's rule is talking about are expressions where you cannot infer the value from the symbols on the page. So we've all heard, for example, that you can't divide by 0, right? Dividing by 0 is a no-no. But throughout the semester, we've bumped into a whole bunch of expressions like 0 over 0, right? If you take any of those limits that define the derivative, f of x plus h minus f of x all over h, and you just plug in 0 for h right at the start, the top is 0, the bottom is 0. Other weird looking things that we've seen, infinity over infinity, right? Back in section 2.6, when we talked about limits at infinity and horizontal asymptotes, a lot of the things that we were working with back then, if you just plugged in infinity for your limit, the top went to infinity, the bottom went to infinity. That's a little bit wonky. Another weird one, infinity minus infinity. 0 to the infinity. 0 to the 0, 1 to the infinity. I'm sure I'm missing one here, etc., are called indeterminate forms. They're kind of like things you can write down using algebra symbols and numbers that live outside of what can be understood with those algebra symbols and numbers. In each one of these expressions, you've got kind of two forces fighting each other. I don't mean forces in the sense of physics. I mean, for example, in 0 over 0, the bottom being 0 wants to make the whole thing huge, right? Like if I divide 1 by a number very, very close to 0, try it, you get a huge number. If I take 1 and I divide it by 0.0000123, we're going to get a big ass number. But if the top is also 0, that wants to make the fraction very, very small. So the bottom being 0 wants to make the fraction huge or infinite. The top of the fraction being 0 wants to make the fraction small or 0. Normally, any fraction with 0 upstairs would be 0. Normally, any fraction downstairs with 0 would be infinity. But if they're both 0, those things are fighting each other. You can think of the same thing with 0 to the 0. Any number whose base is 0, like 0 squared, 0 cubed, the square root of 0, 0 to the 1000, 0 to the pi, should all be 0. But any number raised to the 0th power should be 1. So these guys are fighting each other. The base here wants to make the whole thing 0. The exponent here wants to make the whole thing 1. So these things, which are called indeterminate forms, are built up out of numbers and algebra operations in such a way that the two objects are fighting each other so aggressively that you can't tell what the value of the expression might be. They arise from limits. For example, when we looked at the limit as h goes to 0, sine h over h, if you just plug in we get sine of 0 over 0, which would be, well, sine of 0 is 0. which is a problem. Now, we did see using geometry and the squeeze theorem that in this particular case,